So if we look at a common gate amplifier, that is one that has the gate at some value VGG, a DC value. The signal is on the drain. Let's write those names in. In the source, gate, drain, source. So the signal is on the source. The output is still on the drain. Our input resistance is right here. So to analyze whatever circuit, generally we want to start off with finding those small signal parameters based on the DC parameters. So I think this is the same as the common source that I just gave. Over V overdrive, 2ID over V overdrive, we've got ID and we've got V overdrive, so we can use those two. If we put those in, we get 2 milliamps. Let's write it out. We get 2 times 250 microamps divided by 0.25 volts for V overdrive. That gives us 2 milliamps per volt. And for common gate, it's important to know what 1 over GM is. I'll show that in just a second. And so 1 over GM is 1 over 0.002. That's 500 ohms. We could figure R naught. It would be the same as we had before. It's 120K, but I'm not going to use it. If we substitute the T model for this transistor, so we just pull out these terminals, what's inside the gate, drain, and source, and plop in the T model, which is always better when we have something on the source. We want to use the T model. So if we do that, we've got a T model for the common gate. And again, we have the gate, the drain, and the source is down here. And remember, with the T model, there's no current going into the gate. So all the current is going through. So now we just found the GM was 2 milliamps per volt, and 1 over GM is 500 ohms. So we can put that in there. We've got a 500 ohm resistor for 1 over GM. Otherwise, we've got the same resistance, 15K in the drain, 25K in the load, and now we have a 20K signal generator resistance. So again, the output is the same configuration as we had before, but maybe it looks confusing with this this T model. I don't know. So you could redraw it. If it's less confusing for you, I will always tell you to draw things equivalently so that they make sense for you. And as I said, we're going to skip R naught. We're not going to include R naught here. Oops, I don't want that going to ground there. So we've got R load is equal to 25K, and we've got RD here, and that's 15K, and we got V out. At that node, I'm not going to. We got V sig, we got 20K, 500 ohms, and that's ground there. But the main thing you can notice is that these two are in parallel. In fact, even though they might look kind of strange up here, they are in fact in parallel, just like it was before. So on the common source, so R out is what the load sees. So that's what this sees. What the load sees is looking into here. That's R out. And R out is just simply seeing, or the load is simply seeing 15K. So R out is 15K. But the input is now on the source, and the input resistance is definitely not infinite as it is in the common source, but it's easy to see. Let me just change that color. I want to have red there. It's clear that what the signal generator sees for Rn is looking in. Well, we're just looking right into here to ground. All right, we got ground on the gate, and so Rn is just seeing that 500 ohm resistance, and Rn is just 500 ohms. That's 1 over GM, and you could see that if you look up on the table of everything. Now, if we leave off GM, AV naught, the open circuit voltage gain, would be plus GM RD. So that's 0.002 times 15,000, 15K, and that gives us plus 30 volts per volt. That's the open circuit voltage gain. That's without the load resistance. If we include the load resistance, then we've got these two in parallel, just like that, just like I went over. So if we include the load resistance, so then we have AV, that would be plus GM times RD parallel with RL, which is actually the same as the output resistance. Well, no, it's RD, yeah, so it's 15K, so it's 0.002 times 1 over 15K plus 1 over 25K. And if we run that through, we've got plus 18.75 volts per volt. So that's quite a drop in the resistance when we include this 25K resistor. Quite a drop in gain, but that's just how it is. Now, for GV, we need to find what VN is. VN is what we have all the way back at the input. VN is right back here. And that means we have a divider to ground. We got the 20K resistor and the 1 over GM resistor looking from V sig right to ground there. And so we've got to account for that. If we look at what this value of VN is, we could just draw this divider. Let's see. We'll draw ground there, and then we've got V sig, and VN is right on this node. $500 and 20K. That is 1 over GM and R sig. So that's kind of upside down and goofy, so I could draw it this way. Got 1 over GM, it's 500 ohms, and R sig is equal to 25K, and VN is right here. Oops, sorry, that's V sig. V sig is here, so VN is right there. Look at that and convince yourself that all three of these things are really equivalent ways of saying the same thing. So that means that VN is just that divider of 1 over GM over 1 over GM plus R sig times V sig. And if we put the numbers in, I got 500 over 500 plus 20K. That's 20K right there. Over 20K times V sig, or 0.024 times V sig. That's actually quite a drop. So then we need to multiply that in to get the overall gain. So, but I can write the equation V out would be GM times RD parallel with RL times 0.024 V sig. That's what the entire gain would be. So then we can find GV, the overall gain would be V out over V sig. And that's GM RD parallel with RL times 0.024. And if we put those numbers in, we get 0.46. So our amplifier is making the output smaller than it was from the signal generator. That might be considered a disaster. I mean, what the heck good is this thing? So the problem is that our sig is just so large here. This amplifier isn't suitable for a case where we have a large signal generator resistance. It's suitable for a much smaller one. So what if we had our sig is equal to 100? Then we would have V out, or Vn, I should say, is equal to 1 over GM over 1 over GM plus R sig. And if we're using the same values, then we've got 500 over 500 plus 100 times V sig. And that equals 0.833 times V sig. That's a lot better. If it was 500, for our sig is equal to 500 ohms, and then Vn would be 500 over 500 plus 500, or 1/2. And as it gets bigger, it's going to just keep getting smaller. If it was 1,000, it'd be 0.33. So it's a problem if our sig is really big. Now we can adjust 1 over GM to match, and that'll help. But we've got limits in what we can do. But if our sig is equal to, say, 400, and that needs to be equal to 1 over GM, which would be one way, then we could say GM needs to be 0.0025. And so then we could say, okay, that needs to equal 2ID over V overdrive, or that equals mu n Cox W over L times V overdrive, or that equals square root of 2 mu n Cox W over L times ID. And we've got some choices here what we could change. You could change V overdrive and ID to get that GM we need. You could change W over L and V overdrive to get what we need. You could change W over L and ID, but don't change everything, right? You could really run in to real problems. If for instance, well, let me just say there's some limits. If our sig is equal to 20K, and we want that equal to 1 over GM, then we need GM is equal to 50 microamps per volt, and then we would have a gain of AV is equal to GM RD parallel with RL, and if we put those numbers in, we get 0.469 volts per volt. So another disaster on gain. We can't match this amplifier for a high R sig. It's just not going to be suitable for most situations. And the GV will get even worse. GV would be the overall system gain with 0.23. It's even worse. So it's just a disaster. It needs to be relatively low R sig, and we need to be able to get 1 over GM to a similar or smaller or small range that's similar to that, to not lose too much. Otherwise, it's a very good amplifier, and there's a lot of useful things like this. What would some of the design choices look like if we had 1 over GM, go back to that one, is equal to 500 ohms, then we need GM is equal to 0.002. If we needed the 1 over GM to be 400, then GM is equal to 0.0025. And we could, for instance, say, okay, we'll stick with 0.25 overdrive. So then, so GM is equal to 2ID over V overdrive, and so then current would be 313 microamps. But now R naught, which is VA prime times L over ID, it was 120K. Now it's going to be 20 times 1.5 over 313 microamps, and it's 95K. That's a big drop to go from 120 to 95K, and it might become the fact that we might have to include R naught here. Right here, we might have to include R naught, and we lose a lot of power of this amplifier. So a better choice would have been to reduce V overdrive. So V overdrive is 0.2. Then ID is equal to 0.0025, that's our GM, times 0.20 over 2, and we get 250 microamps. That's the same value that we had up here. It was the same value that we had back for this original version. So we've got 250 microamps. In that case, R naught is no change, and W over L is no change. If we can reduce V overdrive, it's almost always the best choice. But the problem is about 0.2 is often about as small as we really want to go. Sometimes you can go a little bit smaller, but sometimes I'll give you homework that works out that way. But usually that's about the smallest. But